Hi, and welcome to the Glendale Community College Virtual Planetarium. We are in Glendale, California, in the USA, sitting under Skyscan simulated sky. The middle of the starlit circle before you is the view directly overhead. The sides of the circle are the horizons. North is at the top, south is at the bottom, east and west are on the sides. It is late at night, and there are quite a few stars visible. Tonight we'll talk about color. The color of stars, that is. There's a good chance you have heard an astronomer talk about red stars and blue stars. So where are those stars? Most of what we see here is yellowish and white. Let's start with this. A star's color is determined by its temperature, and the color coding is not what you might expect. We all know that red glowing coals are hot, but in astronomy we refer to red things as cool. So you may ask, if red-hot coals are cool, then what is considered hot? The answer is something that is so hot that it turns blue. That sounds strange at first, but think about the temperatures involved in welding. The flame coming out of a welding torch is blue. You can think of it this way: red is hot and blue is hotter. So now we know that cooler stars produce red light and hot stars produce blue light. The reason we don't see red stars is because red stars produce more colors than just red. They also produce yellow, orange, blue, and every other color in the rainbow. The trick to understanding star colors is to understand the proportions. Let's start with a relatively cool star by star standards. The graph shows us the fraction of visible light a star produces in each color. We are only looking at visible light here. We are not considering what happens in the infrared or ultraviolet. The visible spectrum is broken down into colors, and the percentages of each color can be read off the axis. The number at the top of the graph is the temperature in Kelvin. That's degrees Celsius plus 273 degrees. 2,500 Kelvin is kind of hot. The numbers under each bar are the wavelengths of each color. Wavelength is something we measure, so we don't have to worry about one person identifying a color as red and another person identifying it as red-orange or orange-red. The most prominent color here is red, so you might expect the star to be a bright red. But we can't just pick the color with the tallest bar. To learn the true color of the star, we have to mix all the colors in the right proportions. Here I would add 36% red, 23% orange, 17% yellow, and so on. The result is a much more orange star. What happens if we raise the temperature? At 3,500 degrees, we get more orange and yellow light, though the peak color is still red. When we mix all these colors, we get a much more yellow star. Can you guess what will happen if we raise the temperature by another 1,000 degrees? Feel free to pause the video and sketch the graph you might expect. Did you guess right? If not, don't worry, you'll get the hang of it soon. Now it looks like our peak color would be red or orange. What color will we get when we mix a lot of red, orange, and yellow with some cyan and blue and a little bit of purple? Did you expect a very light yellow? If we had mixed all the colors in equal amounts, we would have gotten white. Because we are short a little bit of color on the blue and purple end of the graph, we have a slightly yellowish color. Now let's crank up the heat some more. Look at this graph. Your first guess might be that our star should be green because its peak color is green. Actually, its color is pretty close to white. If we continue raising the temperature, our bar graph starts to get taller on the blue and purple side. Looking at the peak in this graph, you might expect a blue star, but we already know that's not going to be the case. It will be almost white. Finally, we raise the temperature so that the purple bar is the tallest. Now you know better than to expect a purple star. We can keep raising the temperature, and at 11,500 degrees, the white star may look a little tiny bit blue if you squint and try not to look at anything else on the screen. So the point is, every star you see is putting out a mixture of colors, so they never look exactly red or purple or green. This should settle the matter. But wait, what about all those colorful pictures you see in books and on posters where there actually are green and purple stars? I mean, some of those pictures come from NASA or ESA. This poster is a good example. All these pictures are of our sun. They have strange colors because many of them were taken through colored filters. That's a little bit like looking through colored glass. If you look through a piece of green glass, the world looks green. That's because the glass is stopping any other color except for green from entering your eyes. There's another case where colors can be a source of confusion. Take, for example, this image of the Pinwheel Galaxy. If you remember the Pinwheel Galaxy from our videos on galaxies, you'll note that it was not these colors. This image was taken by the Spitzer Space Telescope. The Spitzer takes pictures in the infrared part of the spectrum, which we can't see. Our experience of infrared light is the sensation of heat. For us to see the image, NASA takes infrared colors, which we can't see, and replaces them with colors we can see. If this practice sounds deceitful and unbecoming of a scientist, think about it this way. When you go to the doctor or dentist, they may send you for an X-ray. Then they look at the X-ray image. But we can't see X-rays. What the doctor looks at is the black and white representation of X-rays. You can look at your X-ray in any color you like and still get useful information from it. There's no harm done as long as you know what you're looking at. With that, I'll leave you to look up at the night sky and appreciate its beauty. It's not such a bad thing that the stars don't look like spilled multicolored sprinkles. Sometimes we all need a break from the brightly colored, loud, chaotic world around us.